Ron McNair, and pilot Mike Smith.
Mike Smith shaking hands with the closeout crew, which has assisted him in getting ready. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Engines throttling up. 3 engines now at 104%.
Challenger, go at throttle up.
Challenger, go at throttle up.
1 minute, 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
What you just saw, the destruction of the Space Shuttle Challenger in 1986, was no accident. It was a result of a normalization of deviance. I'm astronaut Mike Mullane. I'm a West Point graduate, but took my commission in the United States Air Force. I'm a combat veteran of Vietnam, and I flew 3 times on the Space Shuttle. Welcome to my safety program, Stopping Normalization of Deviance. That's an odd term, normal, deviance. What does it mean? Normalization of deviance is that natural human tendency, particularly in pressure circumstances, to want to take a safety shortcut. The pressure you may be under is family pressure. There's something going on at the home that's putting you under pressure. Could be budget pressure. Schedule pressure is certainly a huge hammer. But it is a very human thing to find yourself in a pressure circumstance. You have a job to do, and that job may involve hazards. You have safety standards that are expected of you in executing this job. But now you rationalize that because of this pressure you're under, you're not going to be able to do that job and meet those safety standards. It may be a situation something like this. You have a job to do in the plant or the refinery. It involves hazards, and you know you're supposed to wear protective equipment to do it. But you rationalize, that's going to take time, and I don't have time to dress in that protective equipment. I have to get home to take the kids to the ball game. I have to get on to my lunch break. I got to get on to the next job, whatever. And you say to yourself, well, I've also done this job 1,000 times in the past, and nothing bad has ever happened. I can certainly do it this one time without wearing protective equipment and get away with it. And that's exactly what you do. You take that safety shortcut. And what happens? What are the consequences of you doing that? There are none. There are no bad consequences immediately. You get the job done, you're not injured, the boss doesn't call and scream at you, you get on to your lunch break, you get on to the next job, you get home to take the kids to the ball game, whatever. There's a happy outcome all around. What's that going to do? It's going to start forming this false feedback in your brain. The absence of something bad happening when I took this safety shortcut means it was safe to do so. So what's going to happen the next time you find yourself in these same pressure circumstances? And there's always a next time. Because there were no negative consequences the first time you took that safety shortcut, you're going to be mightily tempted to do it again. And you do it enough times, and slowly what happens? The shortcut becomes the norm. You get away with it so many times, that loop is reinforced. The absence of something bad happening means it was safe to take the shortcut. That is reinforced over and over and over until the shortcut becomes the norm. Here's where you're supposed to be in meeting standards and doing this hazardous job, in meeting safety standards and doing this hazardous job. Here's where you are. This deviance is now invisible to you. It has been normalized into your behavior, into your actions. And what happens with normalization of deviance is it leads to predictable surprises. And in hazardous environments, as you face in those plants and in those refineries, and as astronauts face in space, a predictable surprise can be injurious and it can be deadly. And if you ever want an object lesson in a predictable surprise, look at Challenger. Challenger was no accident. Challenger was a predictable surprise. Now, before I explain that statement, you first have to understand mechanically what caused the loss of the Space Shuttle Challenger. Challenger was a result of the failure of the right-hand solid rocket booster. These things are 150 feet long, 12 feet in diameter, and each of them weighs 1.3 million pounds. They're made in Utah. You can't transport an object that large from Utah down to Florida where it's launched, not as a single piece. So they make the boosters in 4 propellant-filled pieces that are shipped separately by flatbed rail car from the Thiokol plant in Utah down to the vertical assembly building at Cape Kennedy. There, the segments are stacked on top of each other and bolted together to form twin towers of boosters. The gas tank is hung between the boosters. The winged vehicle is attached to the gas tank, and then all of this is taken out to the launch pad on this gigantic mobile launch platform. Now, when these boosters ignite, they burn at 5,000 degrees Fahrenheit and at a pressure of about 1,000 pounds per square inch. Steel boils at 5,000 degrees, so you have to ensure in your design that the steel of the booster is never touched by the fire that it contains. So there's insulating material to run the inside length of these booster segments. The obvious weak point in this design is where you've bolted the segments together, because there you have a potential leak path for the gas to pass to the outside, melt the steel, and cause a catastrophe. Now, I'm not going to go into the engineering specifics of the joint design that was intended to prevent such gas leakage, other than to say it was based on a redundant flexible O-ring scheme. 2 flexible O-rings in grooves at the perimeter of each of these segment joints were supposed to form a steel-to-steel pressure seal to prevent the fire from leaking out. Here is a piece of a solid rocket booster O-ring. The real ones are 12 feet in diameter. They sit in grooves at the perimeter of each of these segment joints. On Challenger, both O-rings failed on the bottom segment of the right side solid rocket booster at ignition. This is Challenger coming off the launch pad. Look in that yellow circled area. You'll see black smoke. That's the vaporized O-rings being shoved out that bottom joint. You now have 5,000 degrees eating into that outer wall. As the rocket flies higher, the gas is vaporizing a bigger and bigger hole in the side of the booster rocket. 73 seconds into flight, the rocket comes apart, killing the 7 astronauts. You'll need that background to understand my comment, Challenger was a predictable surprise. At the time that rocket came apart, killing those 7 astronauts, scattered throughout NASA and their contractors, and filing cabinets and desk drawers were written documents, memos predicting that the exact thing that did happen, i.e. failure of the O-ring, was going to happen. Where did people get the information to make such predictions? From the best source available, flight data. It doesn't get any better than to get the piece back and see how it performed. And that's the case with these solid rocket boosters. They're not throwaway items. 25 miles up, they burn out, they're jettisoned. They have gigantic parachutes that are deployed to lower these things into the water. Air is trapped inside the tubes when they hit the water, so they float. Tugboats are positioned out there to put a line on them, tow them back to shore. There they are cleaned up, taken apart, inspected, and used over again. The operative word in that process is inspected. And on 14 of 24 missions before Challenger, Challenger was number 25. On 14 of 24 missions before Challenger, in the inspection process, quality assurance and safety people noted that the O-rings, which were never designed to be touched by fire, were being touched by fire. And they understood the ramifications of their findings. This design is flawed, it's going to fail, and people are going to die. And they basically put words to that effect in these various memos. I want to share with you excerpts of 2 of these memos, both of which were written by Thiokol engineers, the contractor, to their customer, NASA. The first memo is dated February of 1984. This is 2 years before Challenger. And in part, the memo reads, "The recent experience of 2 burned O-rings on STS-11, and that's the 11th shuttle flight, raises concerns with STS-13. You know, when I read this, I wonder how come nobody was concerned about STS-12, my first mission. I really should check into that. The O-ring leak check procedure is also an urgent concern. Your support in this urgent matter is requested. 2 years before Challenger, the label urgent has been hung on this O-ring design. It's not working." Here's a sentence from a Thiokol memo dated July of 1985. This is 6 months before Challenger. This memo was written by Mr. Roger Bougielet, a Thiokol rocket engineer. In his memo, he wrote a very prophetic sentence, and here it is. "It is my honest and very real fear that if we do not take immediate action to dedicate a team to solve the problem with the field joint," and that's the O-ring, "having the #1 priority, then we stand in jeopardy of losing a flight, a crew, and all the launch pad facilities." Mr. Bougielet's prediction was only off 73 seconds. He thought the rocket was going to come apart on the launch pad, destroy the vehicle, kill the crew, and take out the launch pad facilities. He missed it by 73 seconds. Challenger was no accident. Challenger was a predictable surprise. Now, I know what everybody's thinking right now. Why didn't the NASA contractor team react to these warnings, ground the fleet, and fix the problem? And the answer is they were laboring under a long-term normalization of deviance. And let me explain. Years before Challenger, a standard of performance was established for these O-rings in our failure modes and effects analysis document. In that document, the O-rings were given a criticality 1 label, meaning if they ever fail, it's loss of the vehicle and death to the crew. So a standard of performance was established for these O-rings. They can never show any hint of a failure mode, because if they do fail, it's unquestionable what's going to happen. It will kill the crew. And de facto, you have now established a standard of performance on how the team should react if they ever see a problem with the O-rings. Criticality 1 deviance, if you see a problem with that, you're going to have to ground the fleet. But that standard of performance was established years before Challenger in a no-pressure situation. Emphasis on those words. When the first O-ring damage is seen, it's not a no-pressure situation. First O-ring damage is seen when the boosters come back from the second shuttle mission. Now you have quality assurance safety people staring at their worst nightmare, evidence of a major design flaw in this multi-billion-dollar program. And they can see how the standard of performance has been violated. We are looking at a criticality 1 violation here, a burned O-ring. And at that point, they should have followed and met the standard that came attached for the team to a criticality 1 deviance that said you ground the fleet. But nobody could bring themselves to say those words, ground the fleet, to meet that long ago established standard of performance for the team. Why? Because this wasn't a no-pressure situation. These people are under tremendous schedule pressure, not just to see the fleet continue to fly, but to rapidly expand the shuttle flight rate. It is laughable now to hear, folks, but you know where we were headed in the early 1980s with the shuttle flight rate? 26 missions a year. A shuttle was going to be flying every 2 weeks. And in fact, the shuttle made no economic sense if it wasn't flying at that flight rate. NASA had promised Congress and the American public the shuttle would dramatically reduce the cost of operating in space, and the way that was going to happen, it was going to be so easy to turn between missions. Basically, it was going to be a matter of weeks from landing to getting it out on the pad and launching again on the next mission. And that business model, 26 missions a year, became our God.